Okay. Switch the camera. Okay. So last time we were talking about 5, 3, 5, 4. So 5, 3, I believe, was exponential. And then 5, 4, we started talking about logarithms. You just came by here. Before we get into logarithms, I think it might be good to go over like a few. This thing that we said, if we have like bases, we can think of this. We could write this out if you want. We could write out 2 5 times. I guess I'd do it. It's not too much work. And then I could write 2 out 3 more times. If you want to expand it and write it out and prove it to yourself, if we multiply the bases, we're adding the exponents, right? And so I'm pretty sure we've used this at least. I don't know if we've talked about it formally, but there it is. If you have AM, so use some letters because we're in algebra. This is equal to, it's got to be the same base, and we're going to add the exponents. And so this is what it looks like when we have numbers plugged in. This is what it looks like with letters generalized. The other thing, if we're dividing, well, if we're multiplying, we're adding. If we're dividing, you can probably figure this one out by deduction. Ooh, but that is a to the m minus n. We're going to subtract the exponents. You can do this with expansion too. So if you have like 2 to the 5th over 2 to the 3rd, you can write out 5 of those guys. You can write out 3 of them, and then you might notice have the same thing over itself. Those things kind of simplify out, and I'm left with what? 2 squared? Or 5 minus 3? I guess we can simplify that out since it's numbers. But this is the property that I'm looking at, right? So we have that exponential property, we have that exponential property. And the third one I want to think about is exponents to exponents. And so the way I kind of think about it is like exponents are always kind of a step behind the base. And so if I think about multiplying, the thing that increases things slower than multiplying, or the operation that is defined, within multiplication, we have to use addition to define the multiplication. So this is like multiplication is like a step above the addition in my mind. And so like your exponents are always kind of like a step behind your bases. So if your bases are being multiplied, your exponents get added. If your bases are getting divided, your exponents are getting subtracted. And then we're adding exponents, or we're putting exponents to exponents. You can do this with numbers if you want. I would do it with smaller numbers, 2 to the 3rd, to the, 4th. And so you can write this out with definitions, but this is you have 2 to the 3rd 4 times. I don't want to do this too much. 2 to the 3rd. I'm running out of room there a little bit. But we have it 4 times. You might notice that we're going to have 2 a total of 12 times. And how do you get that? You get that from multiplying those exponents. And so if you're raising exponents to exponents, there's this rule that says multiply the exponent. And there's a reason why I'm starting off with this, and it's stuff that we've kind of used this before. But in order to think about logs, it's really good to think about those exponent rules. Because all those rules that we just saw, we're going to get some sort of analogous sort of rule that's going to happen in the logarithms. It's going to give us some sort of property about logs. And so let's look at a few of these. The first thing says log base a. So a is just the base. It's any real number. It's not log base 1. It's not a very interesting base. So this, if I want to think about this, if I do my circle thing, I think that's how you'll get to it. So this is a base of A to the 0 power is going to be equal to 1. Okay. So we've talked about this rule. Anything to the 0 power is going to be equal to 1. So this rule, I hope, should make sense following from this thing. It's just another phrasing of this rule is all it is. This thing says A to the first power is A. And this is what we know. If there's not an exponent there, we can always write a 1 there. That's basically all that's telling you. Anything to the first power. We could even put a 1 up here, A to the first power. You get that log base of A of A to the first. You get these inverse functions happening here. We're going to get just that 1 out of there. Okay. Okay, so for 2, 3, and 4, I think you can probably see the rule that they're going to be sort of analogous to. This one has addition and multiplication. This one has division and subtraction. This one is kind of like that exponents to exponents thing. Okay. And so maybe think about this a little bit. So we're going to go both ways with this equal sign. We're going to take 2 logs and we're going to combine them to 1, and we're going to take 1 log and we're going to distribute it into multiple terms. I want to give you like a little insight into like how I might solve these things. You might notice M and N aren't in a base A. So like the first thing I would do is I would put them as a base A. So there's some power of A that I can make that will make M. And there's some power of A that I can have that will make N. And so I would do that, and then if you do that, I think it might be a little more obvious. Like you can look at the left side. So we look at the left side, log base A of M looks like log base of A to the K. When we look at the left side, we can rewrite it as log base A to the K. And log base A to the L. Something out of it that looks like K plus L. The right side is log base A of Mn. Well, that's log base of what? A to the K, A to the L. And we can use our exponent property here. And so this is the exponent property, A of what? KL. Plus L. Adding the exponents if I'm multiplying the bases. And if I'm looking at this, this comes out as K plus L. You might notice that left side is equal to the same thing the right side is, and so these two things are equal to each other. And so if I was like trying to prove this sort of thing, this is probably the sort of approach I would take to prove that they are the same thing. Another way, if you want to kind of demonstrate this to yourself, I think you can do weird things. Can you do that? Maybe not. I think you can just take these both raised to like as an exponent on an A, and I think it's to simplify out as well. There's a few more tricks you might have to use to do that. But I'm hoping you realize this is what you're doing to your bases, and these look like your exponents, right? Looks like what happens to your bases, and this looks like what happens to your exponents. And so things inside the log are like a step above things on the outside. And so if we're adding two separate logs, we can combine them with multiplication on the inside. If we're subtracting two logs, we can combine them with division on the inside. This is log of base a to m to the r. So if we have exponents raised on the thing inside the log, we can bring those exponents down in front. All right. So enough talking about the rules. I think like if we get some applications, it might work a little better. And so this says ln, so the natural log of kz. And so they want us to expand each of these things. And so if we're looking at this, expansion means we're going from this thing on the right and we're making more terms. So we're going from right to left in this equation sign. And so if we're looking at that first thing, ln of kz, I'm hoping you see it looks like the product rule, rule number 2. And so if we see this product rule, ln of kz, it says if we multiply these two things inside the log, we can separate them into two logs. One is ln of k, one's ln of z. And the operation between the two is going to be addition. Okay. Same thing here. We have log base 2 of x divided by z. And so this says if we divide things in a log, we have one that's of log 2 of x, we have one that's of log 2 of z. And if this operation is division, this is the quotient rule, number 3. This thing has to be subtraction. Oh, did I not? Okay. I don't think I want to do this. Well, they might have square roots in your notes or in your. So I'm pretty sure we danced around that section that had the things higher than square roots. I think we did square roots. And so if I look at this, I hope you see. I hope you see this. This is what? Square root of x to the third. And so you might notice there's some division in there. There's a square root and there's an exponent. So if we want to break this thing up, okay. If we want to break this thing up, we have to see this division. So I want to do something with this division first. So the thing that I'm dividing is square root of x to the third. That's my numerator. My denominator is the k. And this is log base 3. Okay, so we want to do a little bit of work with these exponents. So I know we kind of glossed over the section with radicals that were higher than 2. I think we talked about base 2 or square roots. If we want to look at this, if I want to look at a square root, if I just do the square root of x to the first power, this is x to the 1/2 power. If I do cube roots, I can think of that as a 1/3 power. And then to continue with this a little bit, if I do things that look like, let's do what, 5th root of squares? This number, you can think of this as 5/1, and where this is kind of like racing exponents, 2 exponents. this is going to be multiplying those things. So if you do 5 over 1 times 1 over 2, it's going to give you x to the 5/2. So another way to think about this is your numerator, this is your denominator. And so we need to be able to convert this thing to exponents. Okay. With that said, this thing should look like x to the 3 over 2. And I'm expanding this thing. And so now if we look at rule number 4, I want to have all logs. I don't want any multiplication, division. And then the other thing, I don't want any exponents in anything. And so this has an exponent. This is x to the 3/2. What I can do with this exponent, grab another color here, I can bring this thing down in front. And so that is rule number 4, the power rule. So we have 3/2 of log base 3 of x. And I guess I put some extra parentheses around this thing. And then we also have log base 3 of k. I'm gonna have to put these brats in a different room. They are distracting. Okay. So I don't know how much the homework is going to focus on these radicals and these powers. There might be a few problems like that in your homework. But I know we did gloss over that section. I think they removed that section where we actually talk about higher power roots, if I remember correctly. Okay. Well, if there's no questions, I guess we'll continue going on. Expand each expression, so still going in the same direction. We see log base 2 of 4 y to the 3rd. If we look at this, we kind of always want to go in order of what it says on the sheet. We want to do the product and quotient rule before we do the power rule. And I guess you could try doing it the other way and see where it goes wrong. But it's not going to work too well if you try to do that power rule first. Order of operations is going to kind of fall apart, and it's not going to end up in the same place. So you want to do it sort of the power and quotient rule before you do the power rule. Did I say that right? Product and quotient before power. Yeah. Okay. Log base 2 of 4 times y to the 3rd. So there's exponents and there's multiplication. So we want to do this multiplication first. So if I want to do the multiplication, I'm expanding this, so I should end up with more things. And so the first thing I see is a 4, and we're multiplying that by a y to the 3rd. So now we're adding 2 separate logs. This is log base 2 of 4. 4 is 2 to the 2nd power. So if you want to do this in your calculator, you could do it in your calculator. You should be able to do this one by hand or in your head at some point, hopefully. It might take you a minute, but it's doable, I guess is what I'm trying to say. This is a number. This should be the number 2. The other thing I have there is there's some exponents there, and the rule is if I have exponents inside my log, I can bring these exponents down in front. And so this looks like a coefficient on that log base 2 of y. And they want us to expand this. There's nothing being multiplied or divided in my log argument. There's nothing raised to exponents in my log argument. That should be fully expanded. There's no logs of numbers in there. I got those simplified. My advice on simplifying these things: if they simplify to an even number, simplify them. If not, just give me the real deal, the ugly thing with the log in it. That's what I would suggest. Okay, so we see Ellen. Question?
Yeah, sorry. How does log 2 turn 4 turning log base 2 4 turn into 2? You divide 2 into 4, or
Log base 2 of 4, so 4 can be written as 2 squared.
okay?
And if that's the case, then this log 2 and this 2 are undoing each other.
Okay.
And I'm left with just this 2 up here. So I know there's 3 2's to pick from, but it's that one. Yeah. After you do these for like a dozen years, it just comes pretty quickly then.
Got it.
Yeah.
Give me a few years.
Okay. This is ln of x y to the third divided by square root of z. And so I'm hoping you look at like when you divide things. So if we're crunching this, the last thing we would do is divide. And so the first thing we kind of want to do is to take care of this division. And so when you divide things, you look at this thing separately from this thing. And so the first thing, I have a xy to the third, and then I need to take an ln of this thing. And I have a square root of z, and I need to take an ln of that. And what I need to do between these two things is subtraction to take care of that division. So division on the inside becomes subtraction on the outside. Multiplication on the inside becomes addition. And I think we had something, this looks very similar to that previous problem. And so I know I don't have it, but you should really put like sort of parentheses around these things. And that's kind of the main reason why right there, is we have that minus or that subtraction sign that we're gonna have to do some distribution with. It may not be an issue with this one, but in general, it might help you in the long run. So ln of xy to the third looks like ln of x, and I'm going to skip a step, but this is plus 3 ln of y. And so this takes care of that side. We still have to subtract whatever the heck is over here. And so I'm going to go a little fast, but this is z to the 1/2 power. So this square root I can bring down as a half. And I'll be left with ln of z. Y'all are brats. Okay. And the last thing there looks like log of square root of 2x plus 1 over x plus 2 squared. So they can do like some weird stuff, I guess, on these things. they can put the power on here. They can do this and group two numbers to a binomial and then put those to a power. Just sort of looking at this thing, we have this and this. This division would probably be the last thing that you do when you're doing order of operations. So if we want to undo this, the first thing we need to sort of do is undo that division. And so that division looks like that thing being divided by the other thing, which is x plus 2 squared. So I'm taking log of my numerator minus log of my denominator. Now we're looking at this thing. First thing I see is log, and it looks like a square root of 2x plus 1. I'll go ahead and write it out. We can rewrite it that as 2x plus 1 to the 1/2 power if we wanted to. But the main reason why I'm writing out this radical is because it's an exponent, and it's an exponent that I can bring down in front. And then don't forget the other half of your equation. This thing has an exponent, and this exponent I can also bring down in front. Now we're looking at this thing. Okay. I'm looking at this thing. I see this 2x plus 1. Do I have a rule for adding inside a log, like this 2x plus 1? And that's usually the first thing people look at. Can I do anything with this thing that's inside of here? If it's on the inside of the log, well, if it's on the inside of the log, we have something for multiplication, division. We don't have anything for addition in the inside of a log. We have it if it's on the outside, we have it adding 2 logs, right? That's a little different than what we have here because it's all inside of our log. So if this is all inside of our log, there's nothing we really have to work with this. There's no rule that we have that we're given that tells us we can expand this in any way. And so I think this is the point where people try to do something with this, but that's it. There's nothing we can really do with this. Where we have something that's addition inside of a log, there's no way to really expand that on the outside. Maybe you see like this multiplication, because I mentioned something about if there's any multiplication in there. There is a 2 times x here, but then if we look further out, there's a plus 1. And so the last thing you did was plus 1. And so this addition makes it to where there's not really a whole lot we can do with that, right? It's being attached into this addition. And so at this point, I think that's about as far as you can expand this thing. Questions about these? I will say you can sit here and watch me all day. It's not going to help you very much to learn these things, though. These are things you're going to have to practice. They're going to take a little bit of time. Okay. Number 3. The equation y equals bx to the a is involved in applications involving biology. Another form of this equation is, and so they took this, the other side of this is the log property, or the log equation. Use properties of logarithms to obtain the second equation from the first. Okay. If we have y equals x to the a, this is the log of y. So if we want to take the log of y, we take the log of the left side. We should also take the log of the right side. And now they want us to show that this right side is also equal to this thing using our log properties. So we have the left side here. Now we just need to show that this thing is equal to this thing. Okay, so we want to use our log properties. This is log of bx times b times x to the a. This is, first thing I see there is a multiplication of a log b and a log of x to the a. So b times x to the a is multiplied. We can separate them with adding two logs, two separate logs. So multiplication on the inside is addition on the outside. Multiplication on the inside is addition on the outside. I'll say it right. And then this is one last thing we have to do. This is log b. This has an exponent. We can always bring the exponent down in front. And I believe if we do that, we have the equation that they have there. Log b plus a log of x. That's it. Okay. So far, we've been going right to left. We've been taking a single log and we've been expanding it into multiple logs. Now, we want to go left to right. Now we're going to take two logs and we're going to combine it to a single log. And so we have two logs. They're being combined by addition. So addition on the outside. Excuse me. Addition on the outside means we are multiplying on the inside. And so this has to be multiplication. Oh, I set that up a little cheesy. ln of, and this is multiplication. This is all multiplication. So you might notice like we can do the commutativity. Commutativity. We can rearrange these things so that we have like 3 times 4 will give us the 12. And we have this thing e to the second times e to the negative 2. And so if we have like bases, you might notice we're adding exponents, but this is going to end up giving me e to the 0, right? And e to the 0, or anything to the 0, is just a big fancy 1. So that's not really doing anything. And so really what I'm left with is I don't really have those e's there anymore. I just have the ln of 12. Okay. So, example 4, log 4x plus log of 2x. Same thing, if this is addition on the outside, I want to go to multiplication on the inside. And so I have log of 4x times 2x. And so 4 times 2 is going to give me 8, and then the x times x will give me x squared. And we're looking at this, we want to combine it to one log. We got one log.
We wouldn't put 2 log 8x.
You could do that. Here they want it combined to one log, and so that would be good enough. And let me double check my notes and make sure that's what they say in the book. Yeah, I would leave it actually as the way I have it. Because when we're doing expansion, we want to bring this thing down, and when we consolidate it, we typically put it back up there.
Okay, thanks, man.
Yeah. But technically, if you had one log and you brought this down in front, you're still making one log. I wouldn't count it wrong. It would still be one log.
Okay.
And really, like, they're trying to get to something here. There's there's always like some sort of like future goal in the math class, but what we're trying to get to is solving these things. And if you can get them down to a single log, whether this 2 is up here or down here, it's not going to make like a whole lot of difference with what we're doing. You can solve
Okay.
it. You can solve it fairly well either way, I guess, and that's where my side is.
Okay. Thank you.
Sure. And so the last one, we have this, and we don't see powers. We can always write a 1 up there. So we have log base 2 of x to the 4th minus log base 2 of x to the 1st. And we are subtracting 2 logs. We've done plenty of addition. Now they want to throw a subtraction 1 on us. We're subtracting 2 logs. We can combine them as 1 log with some division in there. So we're dividing those 2 things. Now we're looking at our exponent rule. This is log of x to the 3rd. And let's just put parentheses around the thing so you see what is actually in the log. Okay. Write this expression as the logarithm of a single expression. So we're still doing the same thing, combining logs into 1 log. And so we still want to do PEMDAS. We want to go left to right. And if we do PEMDAS, you might notice it matters here. If we do this before we do that, we're going to get a different number. And to kind of prove it to yourself, you can throw away the logs. You're going to get a different number if you subtract these 2 before you add those 2. No, wait. Maybe it won't. Yeah, I don't think it'll matter here. So typically we want to do things left to right, addition, subtraction at the same time. And so we're looking at these. These are adding. So we're adding 2 logs on the outside. If we're adding them, the operation we want to do is multiplication on the inside. So addition on the outside is multiplication on the inside. 9. So you can do these in a little bit different order. But I think the first thing we can do is 6 times 3 is going to give me that log of 18 minus the log of 9. And if I look at this, I have 2 logs. They're being combined by subtraction. So subtraction on the outside is division on the inside. And if subtraction on the outside is division on the inside, 18 divided by 9 is going to give me 2. 2. And so log of 2, it's not going to give you a pretty number, so I would just keep it as log 2. That is the most exact sort of solution you can give me on that one. Okay. So the last time when we were expanding these things, we did product and quotient before we did the exponents. And so now we want to think, and we want to do the exponents before we do product and quotient. And so if I want to do these exponents, I have 4 ln of x. That's going to give me an ln of x. And instead of writing it out in front, now I want to write this thing as an exponent. That's going to give me ln of x to the 4th. It'll be subtracted, and I'm going to have another ln. 1/3 of ln of y. That's like y to the 1/3 power, or instead of a 1/3 power, you can tell me cube root. So maybe I'll write a little middle step. Y to the 1/3 power is the same thing as a cube root of y. And the last thing is plus, and I have an ln. And I have a half in front of that ln, and so that half is sort of like a square root. Well, not sort of like it. It's exactly like a square root. And so a half power, or this is z power. And so now we got all those exponents taken care of. The next thing is to do these things PEMDAS, left to right. And this one, I believe, if you do the addition before you do the subtraction, it will definitely not be the same, I'm pretty sure. So this is ln x to the 4th minus this. So if we're looking, and maybe I should really put these things in parentheses to do it at home. We have this thing being divided by this thing inside one log. X to the 4th, this is the cube root of y down here. This gives me my top, this gives me my bottom. My internet connection is unstable for some reason. Google Fiber don't like me no more. Plus, we still have that plus ln of the square root of z. And so what we see here, here's a log, here's a log. What separates them is addition. So addition on the outside is like multiplication on the inside. Okay. So this x to the 4th, this is cube root of y. This big long quotient here. We're multiplying now by a square root of z. If you want to write square root of z over 1, that's fine. But like I think the main important thing at this point is that you realize if you're multiplying it, it gets multiplied to the top, right? This is kind of like we have it out on top, we can bring it out in front. It's the same thing either way. And so this ends up being put on the top, ln of x to the 4th square root of z over cube root of y. Okay. Okay, similar thing here. So the first thing we're going to take power. The first thing that we want to do is the power rule. So if we see something in front, this is log base 5 of x. And now this x is going to get raised to the 6th power. Log 5 of 4x minus log 5 of z. And we're doing z to the 3/2 power. Yes. Okay. I think what I want to do, we need to fix this up a little bit. But I think the first thing I want to do is combine these two things. So I have log 5, have an addition sign here, and have another log 5 here. And so this is log 5. And now this is x to the 6 times 4x. Or we could say what? 4x to the 7th power. Okay. And so thinking about z to the 3/2 power, you can think about this as, it's kind of a silly way, you can think about the denominator separate from the numerator. But 3/2 is 3 times a half. The half power is going to give you a square root. And then the 3, you can either tack it on inside or outside of the square root, to be honest. It really doesn't matter. It's going to be the same either way. And so typically, I'm probably going to write it inside the square root. And maybe I'll throw in that too, just so you can kind of look back at it. This is the 3 over the 2. So this thing on the radical actually gives you a denominator in your exponent. Okay. So I'm running out a little bit of room. I'll do this on the back. Ignore this. Log 5, I have 4x to the 7th. Now I have this subtraction sign I want to get rid of. I want to combine these two logs into one log. And to get rid of that subtraction sign, I have this thing. That's the first thing. That's on top. This thing, the second thing, is on bottom.
Do we need to put the little 2 for square root, or if we just draw the square root, the 2 is implied? Or
Yeah, it's implied. I actually don't need it there. That's fine. I probably wouldn't write it there. I just was copying down what I had written previously.
okay, yeah,
Yeah.
I was just wondering. Thank you.
Okay.
And if it just says log, then also what's implied is 10, right? Is that how it goes?
Yes. Yeah, that's it.
Cool. Thank you.
Are you doing that? They're doing it. Okay. 6 log base 9 of 3 to the 3 to the x. Okay. Square root of this. What was that? Did I write this right? What is this? Okay. Yeah, let's see what's going on. Okay, log base 9. This is a little bit of a weird problem, but I think it might be beneficial to go through it. Log base 9 of this. So the first thing I want to think about is this is a log base to the 3x. And if I have that square root, what that square root is like doing is raising this thing to a half power. And so I have things to a half power. And so if I look at this, best way to sort of separate this is to have 3 to the x to the 3/2. And if I write it like this, I can actually bring this 3/2 down in front. I can simplify this thing a little bit. Not a whole lot. It's not the prettiest. And oh, it's a little silly. I definitely would not expect you to do anything like this. This is straight from the book problem, and for some reason they went through this. This 3, if we're doing log base 9, it's kind of a silly trick. This 3 you can look at as the root 9. Root 9 is 3, or you can say 9 to the 1/2 power is 3. And so we can rewrite this as a 9 to the 1/2 power. And we can bring another 1/2 down. And so this is going to be 1/2 times 3/2 will give me 3/4. This is definitely not something I would expect you just to be able to do from those log properties. But it is something they threw at you in the book. So buyer beware, I guess, on that one. And if we see these two things, those two things are inverse functions. And so what we're actually left with is something that just looks like 3/4 x. But here's the thing. So this does simplify to 3/4 x. Domain. Well, we're still not gonna have the domain restrictions. So it's still gonna be everything in the domain. Is that true? Log of 1 is 0. Yeah. As a quick recap, log of 1 is what? What number is that?
0.
Absolutely. Log of 0 is what?
1.
Ah, no.
Damn it.
Well, let's do 5. 5 to the what power is equal to 0? Does that ever happen? Are we ever going to raise this to? Nah, not going to happen. Does not exist, undefined. Something along those lines, right? That does not happen. We can go 5 to the 0 is 1, right? But we can't raise 5 to something to get to 0. And so this, when we think about logs, we do have to take this into account. This is a domain restriction, right? If it's undefined, we can't use that in our domain. So we do have to look at that, and that's what I was kind of verifying with this. But this doesn't actually come up in this problem. It kind of skates around it. Example 6. That is definitely a hefty example. I don't think there will be a lot of quiz or home or test problems like that one. And so now they're finally giving us, after all that, they're finally giving us, the book finally gives us the change of base formula. And maybe I want to say something right now. Well, it's probably a good point. Paper. talked about like prime factorizations and those sorts of things. Well, there's that fundamental theorem of God. What is that? It's not algebra. It's arithmetic or something. Basically, you can boil everything down to a prime factorization. All the numbers boil down to a prime factorization, and their prime factorizations unique. If I would do 2 to the 5th. What if I look at like this problem? So if you think about like algebra, this would never happen if these were all integers, right? If we get down to prime numbers and we get their sort of integer exponents, we can create like all the integers, right? Based on just prime factorizations. So this doesn't happen with integers, but we can have, and you've seen it, we can have fractional powers. And if we can have fractional powers, we can figure this thing out. And so if I wanted to do this, if I wanted to do this problem, I see there's a few ways to do this, but my approach is the first thing I see is this thing. I want to get something out of a base 2. And so what I would do is I would take a log base 2 of both sides. And so if I take a log base 2 of 2 to the 5th, and I take a log base 2 of 3, and I don't know what that is, it's what I want to figure out, so let that be my variable x. So what power on a 3 is going to make it equal to like 2 to the 5th power? And just for reference, 2 to the 5th is 32. And so if I'm looking at this thing, I believe I can solve this with everything I have now. This log base 2 of this, I believe it's going to give me, 5 over here. It's going to be x. It's going to give me a log base 2 of 3. So I can bring this exponent down in front. And now if I look at this thing, if I look at this, that's going to have two different, that's basically the change of base thing that we're getting at, right? Big log over little log. So I'm not sure if this is exactly why they named it the change of base formula, but in my mind, this probably has something to do with it. We're going from a base 2 to a base 3. How do we do that? We're going to have to use a change of base formula in there somewhere. So we would have to do 5 divided by whatever that log 2, log 3 base 2. So there is actually a number. We could probably guess it because 3 to the 3rd is 27, 3 to the 4th is 81. So we could probably guess it's between 3 and 4. 32 is between 27 and 81. So this would, the power on 3 would have to be between 3 and 4. So this is going to be 3 and some change here. So let's do it right quick. Log 3 divided by log 2 gives me that number, and then I take 5 and divide it by that. So this should be giving me like 3.15468. Almost pi. Which hopefully makes a little sense. Because if 3 is going to 27 and 4 is going to 81, it's going to be a bit closer to 3. 32 is a bit closer to 27 than it is to 81. So you can kind of guess where these numbers are going to be a little bit. But there you go. If we have fractional powers, we can absolutely like go from one base to the other. It does not work with exponents, but it works with fractional powers. And so I imagine that's probably somewhere where this name came from. We're changing the base. And so they say log of b over log of xa. And so they generalize this thing, and I think I mentioned it last time, but we can do log of x over log of a. So if you like the logs, go with the logs. If you like the LNs, You can do either one. It doesn't matter what base. Typically, typical calculators only carry these two as the base. Some of them will actually do different number bases. You got to get familiar with your equipment. And so this is calculator check time. Log of 33 over log of 6. If we do those two, let's just do them real quick. Log of 33. I think this should give me somewhere around 1.9514. And then this one. So this one, I think they might be trying to get you at like maybe order of operations, but I'm hoping you realize you have to do the logs before you do that subtraction. So if we do that, this is like 2.58496, somewhere around there. So that's the left log 6 over log 2. And then the other thing is log 39 over log 7. And this is giving me like 1.88269. And if I do 2.58496 minus 1.88269, it's going to give me about 0.70227. And in general, like a sort of, I know it's an overgeneralization. Sometimes it might be different, but as a sort of generalization, like probably like 3 decimal places is pretty good. I just need enough to know that you know enough. Okay, and maybe I might want to point this out. On my old notes, I had the number 67, so if you printed out your notes before like yesterday or last night, yesterday afternoon sometime, you might want to check this. I would much rather you do 9 and 49. I think you'll get a lot more out of those problems than that other one. Any questions?
This is, I guess this question is unnecessary, but I flabbergasted is a fun word to say. In the sense of example 7, letter A. Why does that work? Like that's crazy. I mean, I understand what you did. I understand how you got the answer, but how does dividing the log of 33 by the log of 6, I don't know, it just seems like it's like, well, that's how it goes. So bang, but there's no like explanation of why that. You know what I'm saying?
Yeah, that's a good question.
You're awesome, Tim. Thank you for those questions.
Thanks, man.
It seems kind of crazy. I'm pretty sure there's like some proof we could probably do that involves like the exponents, you know. But I feel like the thing with that is if I like try to prove it or demonstrate it, like that's probably going to be more convoluted than just like saying, hey, this is a property. And like I absolutely like agree with you. Like you're being a good mathematician by asking that question. Like 100%. I agree with you. Like, there should be some reasoning behind why things are the way they are, right?
I would hope so. But yeah, but I understand that. I would understand that. Yeah, explaining it involves even more math, is what, and we would it would have a hard time following it, is what. So yeah, I get.
Yeah, I'm trying to think of the best way to describe that. And to be honest, I'm not sure if I've seen it myself. It might have been one of those things I just kind of took for granted, without actually looking how it was proven. Um, so I'll try to look into that actually. That's a pretty interesting question.
Oh,
And I'll see if I can give you a good simpler answer or how convoluted it gets. I don't know. But I'll check it out definitely.
yeah, thanks, man.
Yeah. Anything else? I think I'm gonna stop on the record.